And we can begin with some pretty good news. Abdullah, is it correct that the grades are published now for the midterm?
No, they're not published. They're just I think it's done on Gradescope. So
Okay.
to be honest, I haven't published. I don't know how to do that, but I can figure it out if you want me to publish them.
Okay.
Yeah.
So by the end of the class, or sorry, at the end of the class and some minutes afterwards, we will get your grades out to you for the midterm. And the good news, as you can see from the histogram, is that the vast majority of you got A's and most of the rest of you got B's. So pretty good shape there. There are a few people who are out in the tail who are struggling a bit with the exam. And if you're one of those people, please come talk to us. Bring yourself to an office hour and let's have some heart-to-heart about what was getting away from you and how we can, first off, help you understand it right there. And secondly, how we can get you on the right path so that doesn't happen for the second midterm. Okay. So, but overall, vast majority of you did really well. I'm super pleased about this result. Okay. And again, your stuff will be published very soon after the end of the class. Reminder.
I just published it. Sorry to interrupt. I went to radio. Yeah.
Great. Okay. Thanks, Abdullah. I appreciate that. For those of you that are currently here, I'm going to ask that if you do take a little look-see, please come back as soon as you can, because this is going to be another hot and heavy lecture. So I don't want you kind of focused on your exam at this point. So, all right, other items of interest. Homework 5, again, reminder, is due on Sunday night, not Friday night, as usual. We gave you an extra 2 days because we started it late. Okay. This coming Monday, there is no lecture. However, I will definitely on Monday, or maybe a little bit before, have pushed out some new scikit-learn, Jupyter Notebook demos for you, particularly this giant one on support vector machines that I hope you all will play with, because I think it really helps to get your hands dirty and start twiddling the knobs of a support vector machine and see how it changes the results, because I can kind of cement how things happen in your mind. All right. So that's all coming up. So after today, our next regular lecture is Wednesday. Okay. A quick little announcement. The Data Science Student Society sent me this. There are a bunch of, team projects that people in the society have been working on in collaboration with a bunch of commercial data sets, and in some cases with the help particularly of the companies that made those data sets. So if you're interested, I think you should take a look at the showcase. The results of all of their projects are going to be presented. It's on February the 22nd, 3 to 5 p.m. Clearly, some of that clashes with this course, but the rest of it you could go to. And I've also been assured that this stuff is going to be recorded, and/or there's going to be Medium blog posts and stuff like that about it. So worth your while, right? As you all are getting into, heavy-duty machine learning, you might already be at a place, or at least after this class, you should be at a place where you might want to participate in these kinds of things yourselves. And just as a general broader note, for those of you that are interested in careers in machine learning or data science, I highly recommend that you go do these kinds of projects, get yourself involved in a hackathon, okay? Things like that, because when there's a ton of people applying for a job, one of the things that will be a differentiator is I've participated in all these hackathons and data science projects, okay? And besides, you'll learn a lot and you'll meet a lot of cool people. All right. So today we are going to continue on with the support vector machines. In particular, I hope to at least start by the end of the day on this thing known as the kernel trick. And the kernel trick is both one of the coolest bits of the support vector machine, and when it gets down into the nitty-gritty details, one of the things that people find quite confusing, right? Like conceptually, it makes a lot of sense because it's not a lot of difference to what we did when we did polynomial regression, right? We turned linear data into polynomial data. We made a transformation of the data, and that enabled us to use a linear technique to make nonlinear things happen, okay? The kernel trick in SVM is conceptually identical. We're going to take linear data, we're going to transform it using a kernel, put it into a different representation, and in doing that, we can use the support vector machinery, which is a linear decision boundary, and use that linear method to make a nonlinear result happen, to make a nonlinear decision boundary on the transformed data, okay? So we may not get very far on that today because there's a lot of preliminaries and catch-ups, but I just wanted to give you the overall sense of what we're going to try to accomplish here next. Okay, so let's finish up because we never quite did at the end of the last lecture, okay? Let's remind ourselves of what we've learned. The support vector machine is a machine which tries to learn a linear decision boundary in a way which maximizes the margin, which tries to put the decision boundary smack dab in the middle between examples, right, of positive class over here on this side and negative class over here on this side. And as you can see, it tries to both, find that decision boundary, which is right in the middle. Okay, that's the middle line. But it also has these margin lines. And the margin lines are defined by the support vectors. Okay, the support vectors are things which are examples of the closest to each other data points of the respective classes, except for the slacked out variables that we're going to ignore here, okay? Right, so we pick some support vectors. They define the margins, okay? Everything that's outside a margin and is the correct class, so negative class on the negative margin side, positive class on the positive margin side. Anything out there doesn't affect the classification, right? But anything that's inside the margins is going to generate some small loss, okay? Even if it's on the correct side of the boundary, it's going to give us a small loss because it's inside our picked margins, okay? So this is the nature of a support vector machine. It tries to maximize the margin while at the same time it tries to, and this is a conflicting goal, right? Its conflicting goals are maximize the margin and minimize the misclassifications through the hinge loss, okay? So by giving it those conflicting goals, we have a special dial that we can dial back and forth to say which one we care most about. Do we care more about misclassifications and these slack variables here, the ones that are on the wrong side of the decision boundaries, right? This one and this one and this one, right? If we have a high C value, we're going to care a lot about those misclassifications, and we're going to end up trying to draw a decision boundary that has almost no margin, that tries to minimize only the misclassification error, okay? And when the C value is low, then it allows more slack, okay? then it's going to start to ignore things. And it's maybe going to ignore these points here and here and here and draw the decision boundary we're showing here. It's going to try to maximize the margin more. Okay, so C is our dial, which takes us from a harder solution that only cares about misclassification and dials us towards a softer solution on the other direction that cares more about maximizing that margin. And remember that when we make the margin big, we're regularizing, right? It's the equivalent mathematically of doing the L2 regularization on the weights. And so that means that we are introducing more bias and reducing variance, right? We are biasing it towards a simple solution. We're biasing it towards ignoring potential noise things like these guys over here, right? We're biasing it towards the interpretation that there's two well-separated categories that are just noised up, and we want to ignore that noise a lot, okay? So when we have low C, a softer margin, okay, we are high in regularization, which means low in variance, and biased towards finding ultra simple solutions. And when we have high C, our margin is harder, we have little regularization, we have very little to no bias in the system, and potentially we could have very high variance. And high variance in the sense that if you take another draw of the data from the same random process, you could get a very different decision boundary, even though it came from the same underlying process, okay? So let's take a look for a second. Do we think that we understand all the moving parts here, right? We want to maximize the margin when our C value is low, or at least we want to do it more when our C value is low. Opposite, somebody just yelled at me. So let's take a look at the next page. Right? So somebody yelled opposite on the chat. So when the C value is low, that means that this value is low. You are correct, sir. Wow. Thank you. All right. So C value is low. Misclassification error accounts for little. All right. What did I do on the last page? Okay. Low C is the softer margin. It means yes. Okay. Low C. All right. Okay. I was saying it right up until that moment. Thank you, Ahmad. Good. So low C is a soft margin. We care more about is a softer classifier. We care more about the margin. We try to make the margin large at the expense of allowing some misclassification error. Right? And even though Ahmad was not calling me out, but Scott, he actually made me think hard, and that's fine. All right. So again, here we are in terms of the recap. We're going to minimize this loss function, which is a combination of that regularization margin term and the misclassification term, which in particular is set up as a hinge loss, right? Where it hits at 1 and then goes off at 0. Okay. And the reason why we have loss even for, things that are correct, right? These are things that are correct, but they're just inside the margin, right? They are correct side of the decision boundary, but the wrong side of the positive margin. So we get some small amount of loss for things in this area. And over here on this area, this is where stuff is incorrect. And so we get larger and larger loss as we get more and more incorrect. And last time we talked about how we find the derivatives of these, right? It's easy because it's just a two-part derivative. There's the part where you have some loss and it's a constant slope line. So in that case, our derivative is just a constant slope line, constant value because of the line, sorry. And in the case where we are on the correct side of the margin, there is no loss at all. And so there's no derivative. And in the end, what we do is we can train this up using gradient descent. Okay, that is our support vector machine. How is it similar to logistic regression? Does anybody feel like taking a guess at this little quiz? Are they different completely? Do they differ only in one respect? We've got one vote so far.
I mean, I definitely think that they are definitely different in the way you train them, for sure. Like you're using different methods to train them.
What about the prediction side? We now have 2 votes and Chase counts as a half vote there.
I mean, I think that like the resulting prediction can be, because logistic regression, we're still trying to classify into 2 sides, positive and negative cases. And so the predictions are the same in that fact, in that you're trying to predict, like classify into 2 cases, basically, right?
Excellent. Okay, so far, almost everybody is coming down on the correct answer. Okay. What's going on is that the loss functions are different, right? And so during training, that's a different system. But the prediction, right, part is just, is it on the right side of the decision boundary? +1. Is it on the other side of the decision boundary? It's a -1. Okay. And that's the same in both cases. So exactly. Once you've got a trained system, almost all linear classifiers work exactly the same. There's a transfer function. It's a matter of like literally doing a matrix multiplication and a thresholding operation, and that's it. Okay. So trained classifiers of this type, like logistic regression and support vector machines, once you've got them trained up, they are computationally efficient to make predictions with. Okay. This is the training part that sucks. So, but nobody ever cares about the prediction part. That's always quite fast, and that's potentially useful, and often really is very useful in internet-y sort of production environments, right? Where we're just trying to make predictions about face or not face on your camera's autofocus, right? So it's just a matrix multiply. So it's super quick. Your camera, which has almost no CPU, can do it.
So just a quick question. I'm still a little confused about like when we would use SVM versus logistic regression. Like when it came to like the L1, L2 norm, it's pretty obvious when you want to do them, but I'm still confused here why we do one or the other.
So actually, that's a great question, and one which I'm kind of getting towards a little bit in these next few slides, but also like I was holding off on the big comparison until we've got a little bit more of the SVM. But to preview it, right, support vector machines have a couple of things that logistic regression doesn't. Notably, there are some tricks to make them computationally efficient at giant numbers of variables. Logistic regression is order, number of variables, kind of situation. Whereas with SVM, we can do crazy things with the kernel trick that enables us to do it super quick on, 10 million variables. Okay. They often produce fairly similar decision boundaries. Even though they've got very different forces acting on the loss function, because they both, as we'll see in a second, have forces that act on a loss function that, even though it produces the correct classification, but it's just not a good enough, sure enough kind of thing in the case of logistic regression, or on the correct side of the margin in the case of SVM, they often produce very similar decision boundaries. And then logistic regression, on the other hand, one of its bonuses is that it has a probabilistic interpretation, right? So if you want to know how confident am I that this is positive class and not just is it positive class, then you want to go with something like logistic regression. You can add a probabilistic second stage to an SVM, but at that point you've taken a performance hit, so you might as well just use logistic regression anyway. Okay, so let's continue on with that theme, right? So the differences between the different loss functions we have seen. We've talked about how the hard loss, the misclassification error, right, is problematic because it has no gradient, okay? And so while it's exactly what we want to minimize, we can't actually do so. So we're always going to have proxy or surrogate losses that we minimize instead, right? We've talked about the perceptron half-hard / hinge loss, right? And it has a gradient, right? At least where we've got misclassifications. Okay, the log loss is got a gradient everywhere. There's no place at which the gradient goes to 0. So it is always differentiable, and it will, as we've talked about, like SVM, continue to penalize things that are correct decisions, but are just not super confident in those decisions. Okay, now the SVM is another slightly different version of the hinge loss. The hinge now has this area over here that's going to penalize things that are correct decisions, but just not on the correct side of the margin, right? It's going to penalize those classes of things that are right inside here. Right, and once again, it's differentiable, at least on that hinge part, the part that goes up. Okay, bug. So here are all these losses and a few others laid on top of each other. Okay, so the one that says binomial deviance is the log loss. Okay, so right, so as you can see, they all produce reasonably similar results in a classification task, which is either going to essentially be one of these things, right? In a classification task, you're not going to see losses that are out here, okay? You're either getting a -1 because you predicted positive and it was negative, right? Or you're getting, a 0 or a 1, right? As we go the other ways. Okay, and you can see that they lie on top of each other at several different important points, right? Perfect classification, they largely overlap. Okay, So does anybody have any questions we should address about support vector machines, about their concepts and the basic math?
So I'm still a little confused on, I guess, the size of the, not decision boundary, but what's it called? I guess like the error boundary around the decision boundary.
The margin?
Margin, there we go. That's the word I was looking for. So I understand that the size of that is the magnitude of the normal vector, right? Which is the weight vector.
Yep.
Okay, so do we ever purposefully like adjust the magnitude of the weight vector to get more or smaller or greater margins? Or is that what you were talking about with C?
Yes. Right? Okay. So let's take a look once more at the loss function. So what all this stuff, I wish I could clear it out. Okay, you know what? We'll do it this way. Okay. Spotlight thing. Well, that's not what I wanted. Thanks. All right, at any rate, here we go. Right, we've got the weight vector right here. It's a regularization term, right? As this becomes more important when we dial down C, we're going to spend a lot more of our effort at minimizing losses going to go into squishing the weight vector and making it smaller, right? And what we've talked about in the past, if I can just very quickly redraw something, is if we have things that look like this, right? And this is our decision boundary, and these are our margins, right? The weight vector here, its magnitude is by definition the distance to that margin. Okay. So we went through it last time in kind of great detail, and so I encourage you, if you're confused, to go back and review that bit of tape. But the idea here is that definitionally, because this is Wx plus b equals 0, right? And because the positive margin is the same thing but equal to 1, then definitionally that means that the magnitude of the weight vector is the distance to the margin. So when we squish the weight vector and make it smaller, what we're doing is we are expanding the margin, okay? So because this distance in here is, sorry, I shouldn't say it's not the I've said this wrong already today. It's actually 1 over the weight vector's magnitude, okay? So
okay, that's where I was getting confused.
Right.
Okay, so that when that gets
This is,
smaller, then your margin
yes,
gets
so as
okay.
Exactly.
Got you. Okay.
So, and that's why the total margin, this thing we call M, is equal to 2 times the magnitude of the weight vector, right? Because you have one over this way and one going that way.
Cool, that makes sense. Thank you.
All right. So that's the deal, right? We try to maximize margin and, in a potentially conflicting goal, minimize misclassification error. Everything's hunky-dory. All right. So before we get to a kernelized version of SVM, I want to take a little side trip into k-nearest neighbors. Okay. the k-nearest neighbors is useful for conceptualizing the kernelized version of SVM. And then they have, common features that things that are similar, but actually big differences as well. Okay, so nearest neighbors are super easy to understand. Okay, the nearest neighbors idea is essentially just memorize the training data. That's all it is. Okay, you take the training data, you write it into memory somewhere. And anytime you have a new example to classify, you just have to find the k nearest neighbors to that point in the input space. Okay, so the example here, right? So all this data in red and blue are training data points that have labels on them. When we get this new x, then we go out, and if we're just looking for the nearest neighbor, when k is equal to 1, we find the training data point that is closest to that data, to the new x, okay? And we just assign it to the class that is that nearest neighbor, okay? One nearest neighbor. The nearest neighbor method is just find the example in the training data closest in the input space, and we'll use its class. It's just a lookup table, okay? If we do not k equal 1, but k equal to, say, 5, we just find the boundary going out a ways from the data point. We find the 5 nearest neighbors, and we take the average of all of their classes, or, sorry, I shouldn't say the average. We take the mode, right? We count up among the 5 neighbors, and if it's 3 votes for positive class and 2 votes for negative class, then it's a positive class instance, okay? So, exactly, Oscar's got my correction for me in the chat. Mode, it is the most common answer out of all of that, okay? So, k-nearest neighbors is super simple in a lot of ways, okay? So some interesting things about it. It's non-parametric, okay? That means that we're not assuming a distribution. There is no assumption of Gaussianness. There's no assumption of homoscedasticity. There's no assumptions, period, attached to k-nearest neighbors. All right, does anybody think, let's hear some wild ass guesses out there. Because of that non-parametricness, keeping that in mind, does anybody have any guesses about whether k-nearest neighbors has high bias or high variance as an algorithm? The chat is ringing out in favor of variance, which is the correct answer, right? So, exactly. So there's no restriction, there's no bias, there's no assumptions like any of the other algorithms that will tend to bias the answer towards a particular solution. So it's just going to fit the data however the data exists, which can lead to some rather dramatic overfitting, okay? No, this variance enables overfitting. That's the general case of it, okay? All right, so let's take a look at some examples. Here is right out of the hasty textbook that we use as our secondary text. Here are some positive and negative classes, and using one nearest neighbors, just the nearest neighbor to classify, you can see the decision boundaries that come out of this are crazy funky. This is the first time you've seen really an algorithm that is designed to be a nonlinear decision boundary. Well, what happens if we do, instead of 1 nearest neighbors, we do 5 nearest neighbors? What do you think is going to happen to those decision boundaries? Anybody want to guesstimate? We get less funky, less overfitting. Yeah, exactly. I like Scott's formulation of less funky. I mean, more funk is generally better, at least with music, but maybe not with other things. So you can see that the boundaries become smoother. Some of these bizarre little islands go away, right? These little inclusions in here where we had blue examples in the middle of the orange, okay? The decision boundaries are largely contiguous here by 7 nearest neighbors. And if we go with 15 nearest neighbors, this whole island over here disappears as well. Okay, so more neighbors, more voting, more smoothness, more assumptions essentially that there is some noise here and that we want to reject some of the overfitting. Okay. And if you look at, here's a standard kind of, let's check a bunch of different parameters kind of validation curve. Okay. So this is 1 nearest neighbor, 3 nearest neighbors, 11, 21, 151. Okay. The training error is in blue. So the training error starts off at 0, right? Here, there's no way to have any error on the training set because every point is classified and predicted as itself, as the nearest neighbor, right? Once you have 7 nearest neighbors or something like that, if you were going to predict for this data point right in here, you were going to actually probably not predict blue, even though there's a blue in the middle of that orange there, right? So you can start to get some training error as the number of errors, the number of neighbors goes up, okay? And the usual thing is happening here. The validation curve starts off at high error on the test set, goes lower as we get smoother, and at some point gets so smooth that we are, just losing track of the thing that we really want to get a hold of, okay? So this is the underfitting regime. Sorry, this is the overfitting regime, my bad. This is the underfitting regime, and here is our ideal performance level. Okay. So nearest neighbors are pretty cool. Their training is fast. I mean, it's instant. It's literally just writing the stuff to memory, okay? The disadvantage is that it's slow at query time. So we were chatting just a minute ago about the idea that anything that's dot product kind of based, like any normal classifier, like a support vector machine or a logistic regression, is super fast at query time at the moment that we have a new data point that we want to predict, okay? But k-nearest neighbors is the opposite. It's fast at training time and slow at production time, okay? Because we have to do a distance calculation. And if we have to do a distance calculation on 10 million data points, right, then we have to do quite a lot of distance calculations. So it does not scale well with number of training samples, right? When you have very few training samples, k-nearest neighbors is just fine at query time, right? But when you have 10 million training samples, then it's very, very slow. Now, there are tricks to get around this, all right? There's all kinds of things that people have done to make k-nearest neighbors faster at query time with internet-sized data sets. But fundamentally, you're probably, if you're at internet-sized data sets, you're still going to prefer something like a support vector machine, okay? Because all the tricks can only do so much. Okay, another thing you have is that you have parameters in k-nearest neighbors that you have to choose. You have to choose how you measure distance. intuitively, we're probably going to say, okay, Euclidean distance, right, is our base idea of what a distance measure should be. But there are other choices, and there are reasons you would choose different ways to measure distance. We can talk about that in a sec. Obviously, you have to choose your K, which, is the bias variance trade-off again. Okay. But fundamentally, at the end of the day, K nearest neighbors is most limited by its dimensionality. So if you have 10 million data samples, we can figure out a way to make that work with all these computational tricks. But if you have 10 million variables, no, you cannot do K nearest neighbors. All right. K nearest neighbors does not scale with high dimensional data. And that is important to understand. Okay. So just to go with the idea of metrics for a second before we get to high dimensionality, right? There are all kinds of ways in which you can make a metric. Formally, the idea of a metric, don't worry about this slide, okay? If you care, go look it up on Wikipedia, right? But there is a formal definition of what makes a metric. And once you have a metric that hits these things, you can use it to measure distance in many different ways, right? So common metrics you will see all over machine learning is the L2 or Euclidean distance, the L1, which is also called the Manhattan or city block distance, because in L1, if you had a grid, right? L2, the distance between these 2 points is a straight line, right? In L1, the distance goes around the block. And that's why it's called the city block or the, Manhattan distance. All right. So this is L1 and this is L2 for the same 2 points here. Okay. You can generalize that. There's this thing called the Minkowski metric. The Minkowski metric is L sub p, which is, it's the p norm to the 1 over p power. Okay. So the Minkowski metric is a generalization of the L norm setup. Okay. People use that for some sorts of machine learning. There's the Mahalanobis metric, which is a z-score fundamentally at the end of the day, right? So it transforms the data into a Gaussian, and it turns whatever the value of it is into the number of standard deviations away from the mean. Hamming distance, super common in binary features, right? And one-hot encoding is when we turn our categories into a binary feature vector, right? So the Hamming distance is also commonly used, right? So I just want you to be aware that metrics like this exist, that with K nearest neighbors in particular, the metric you pick has a strong influence on the answer. And you would commonly, if you were doing K nearest neighbors on a binary feature vector, you would probably use the Hamming distance, not the Euclidean norm. Okay. Does anybody have any questions on the idea of how fundamental the metric space that you're using is to the idea of a K nearest neighbor? Okay. All right, I don't even care about this stuff. This is the other thing I care about. Okay, K nearest neighbors is fundamentally limited by dimensionality. And it comes down to this, all right? Because for a K nearest neighbors to give you a good answer, you have to be well sampled, right? You don't know anything about the classifications except where you have training data. And if your training data isn't dense enough in your decision space, you can't know what you should call new things that you're trying to predict, okay? If you've never seen something like this before, then you have a hard time predicting from a nearest neighbor situation. So the curse of dimensionality is this. Fundamentally, as you get more dimensions, the density of a fixed number of samples goes down with the power of D. Okay, so as the number of dimensions goes up, the density of your samples goes down to that power. Okay, so if you may think 10 million samples sounds like a lot, but if you have 10 million samples that is supposed to coat a 10,000 dimensional space, that is not a lot of samples. Okay, so the picture on the right shows you this. Let's say there's 100. Whoops, go away you. Let's say there's 100 data points here that are tiling a one-dimensional line. Okay, so it looks really dense, right? To your eye, the coverage of those dots across this one dimension is dense. And if those are accurate samples of the data, the training data, then you could use a nearest neighbors to accurately guess a classification there. So the little red thing here is just showing you half of the space, okay? So half of that space in a random sampling situation, 42% of those 100 dots are in that half of that space, okay? But when we go to 2 dimensions and we're assuming that the dots are randomly distributed among these dimensions, now you can see that inside the half of this dimension and half of that dimension, we're only covering a quarter of the area, right? And therefore, our sampling of that is only 14% of the data dots are inside this half of each dimension space. Go to 3D, we're down to 7% of the data inside the cube defined as halfway along all of those dimensions, okay? And in 4D, it's down to 3%. All right, so you can see the curse of dimensionality is a big one. And if you undersample the area around a new data point, if you don't have training data that's in the nearby region, there's no way you can produce accurate predictions with a k-nearest neighbor. Okay, so, right, here's an example of that. If this is a 1D situation and we have a new data point here, and we're going to get a k-nearest neighbors vote, you can see it's probably going to come to be a red classed object, okay? And it looks like there's a good sampling of data in this region. Okay, but let's expand this to 2D. So this data point here corresponds with that one, and that one corresponds with that one, and that one corresponds, and so on and so forth. So all we've done is we've expanded this out to 2 dimensions. And if our new data point is over here, now suddenly we're in a situation where we feel maybe a little undersampled on the 3 nearest neighbors kind of situation there, right? We don't really have any data over here to tell us what's going on. Okay, so that just one more visualization of the curse of dimensionality. Okay, so now that we have this idea of k-nearest neighbors, we're going to pick up as we're leaving class with the same idea, but in SVM land. Okay, so imagine that we have a kernel, okay? So we're going to take in an input x, right? X is, when we did support vector machines a minute ago, x is just the data that's coming into our system. But we're going to make a transformation of it. We're going to say that we can make a distance metric, okay, between X, our input right now, and some set of landmarks, okay? I'll denote them L sub I. This looks just like k-nearest neighbors, right? What we're going to do is we're going to measure a distance between our new data point and these sets of landmarks, just like we did with k-nearest neighbors, where we used, say, Euclidean distance, okay? Let's start with that, okay? So we'll define our distance in this case to be the L2 norm of X minus a given landmark, okay? Or, sorry, let's do L2 squared, which is actually the Euclidean distance, all right? Or we can take this into probability, all right? So if we make this a probability kind of metric that's between 0 and 1, a natural way to do that would be to take the exponential and divide it by a standard deviation, like so, right? And when we have an exponential like that, let's think for a second what's going to go on, okay? If X is very, very close to one of these landmarks, the distance is basically going to be 0. So in the situation where an X is lying right on top of a landmark, then we're going to get essentially that, right? Which is essentially 1, right? We are highly similar to that landmark, okay? We are going to say that our data point lying so close to that landmark, it must be very much like that landmark, okay? And if we're very, very far away, if our data point is instead, I'll pick this color, right? Over here, okay? Then the distance to that is a very large number, right? So far away is going to be an exponential of a very, very large number. And that is going to be fundamentally close to 0. Sorry. Did I miss a negative sign in there? Probably. Okay. The details of the math, whether if maybe I missed a minus sign, I apologize if so, but fundamentally, this is called a Gaussian kernel, okay? And what I'm trying to write is the idea that you have a Gaussian shape that's sitting on top of each one of these landmarks, okay? And that Gaussian shape is however many dimensions that we're dealing with, right? And we're going to be able to get a similarity measure, right? So kind of the inverse of the distance metric of k-nearest neighbors, where far away is a large number and close is a 0. Now we're going to have a similarity measure where close is 1 and far away is 0. Okay, so we're going to pick up from here next time. As I rather suspected, we did not get very far into the kernel trick, but we at least get an idea at this point of where we're going. So are there any questions I can answer right now? And obviously, you all are free to go, and I will be happy to answer questions for the next 10 minutes about stuff.
So I'm sorry, but I'm a little confused. Is that standard deviation on the bottom, or what is sigma squared? What is that?
Yes.
Okay.
That's a standard deviation measure, right?
Okay.
And it's going to turn into a parameter that we get to dial back and forth.
Okay, perfect.
So,
thank you.
Excuse me, I'm a little confused about the Gaussian curve
Mhm.
if upon that data point. Is that like a Gaussian noise? Or
No. So we're not talking about, oh, well, actually, there is a way to interpret it as a noise function. Okay. So the idea is this. So Scott, this question goes with Chase's actually, in a sense. So when we pick a big standard deviation, we're saying that anything that's even vaguely close to this landmark is potentially the same kind of class as this landmark. And if we pick a very narrow standard deviation that falls off sharply, we're saying only things that are close to this landmark might be the same as this landmark.
So it's
Okay.
kind of almost like choosing the
So
number of groups.
it is similar to choosing the K in its effect. Yep. And it spreads the influence of these landmarks or keeps it close by it.
so the Gaussian, like the x-axis, the horizontal measure is the distance between the two data points, right?
Yeah, I mean, I'm drawing a one-dimensional Gaussian here on what I've noted as a two-dimensional space because I have zero idea about how to draw two-dimensional Gaussians.
I think is a two-dimensional Gaussian is like a circle with different probability.
It's a cone, right? I mean, it's a conic shape essentially, right?
Yeah, I get it. Thank you.
But yeah, the problem here is my artistic skill.
So sorry if I'm mistaken again, but could you almost get like some sort of density or something like that out of this by like summing them up and then like looking at like the value in a certain region?
That is where we are headed. Yes.
Okay.
And yeah, we will see much more of that in Wednesday's lecture.
Okay, cool. Thank you.
Thank you.
All right, if there's no other questions, I hope you all have a really great weekend.
Thank you, Professor. You too.
All right.